While welding with expulsion has been a known issue for as long as modern welding techniques have existed, it's difficult to pinpoint a specific time frame as it's considered a defect that arises from improper welding practices, meaning it can occur anytime a welder overheats the metal during the process, which can happen throughout the history of welding, dating back to the early 1900s when electric welding became more widespread. Essentially, expulsion has been a potential issue in welding for over a century. Yes, in the context of spot welding, expulsion is widely considered the biggest failure because it signifies the ejection of molten metal from the weld nugget, significantly weakening the joint and compromising its structural integrity, essentially meaning the weld is not properly formed and could easily fail under stress. Yes, you are correct. Expulsion, in the context of welding, refers to the forceful ejection of molten metal, and if you weld below the melting temperature, there won't be any molten metal to eject, so expulsion won't occur. These cross-sections were some of the welds I welded during 2003. These welds were made at 200 milliseconds and 11 kiloamperes. The energy used were 4,500 joules. Please note that the interface line are invisible just like diffusion welding. At that time I thought everybody knew you don't have to melt to weld and all cross-section of welds look like these cross-sections. I could not understand why everybody think to weld expulsion free is such a big deal. This is until I did a search about what other people think whether you have to melt to weld. These were the peeled coupons I have made during 2003 to 2006. They were made without feedback loop. From the cross-section of my welds, there was no black dendrite at the center. But you still can peel it and get a good quality weld. Nugget is the little button left after you peeled the test coupon. Before you peeled the test coupon there was only weld and no nugget. After you peeled the coupon there was nugget but no weld. All those coupons were made with a pair of 1/4-inch B cap. The weld time was 150 milliseconds and current was 9.5 kiloamperes. The force was set to 500 pounds. Between 2003 and 2006 I had made about 50,000 non-expulsion welds. I only made a handful of expulsion welds. These welds were made at 300 amperes per square millimeter. After 1000 welds the changes of weld cap diameter is negligible. This is because without zinc coating the amount of molecules diffused from copper electrodes to steel is very small. Spot welding forms when a high current is passed through two overlapping metal sheets, creating resistance and heat that melts the metal at the contact point, which then solidifies under pressure to form a weld nugget. Yes, spot welding involves melting the metal at the contact point to create a weld. Electrical resistance at the contact point generates intense heat, causing the metals to melt and fuse, forming a small spot weld. Yes, spot welding is considered a fusion welding process because it joins metals by melting the base material at the weld area, forming a solid weld nugget. While standard spot welding involves melting metal to create a bond, solid-state welding techniques like cold welding or friction welding can create strong joints without melting the base metals. No, a spot weld, a common form of resistance welding, requires melting the metal at the interface to form a solid bond. The process involves applying pressure and heat to the weld area using electrodes, which causes the metal to melt and fuse together, then solidify under pressure. Ultrasonic welding uses high-frequency vibrations to create friction and heat for joining materials, while resistance welding uses pressure and electrical current to heat and join metals. Spot welding, despite relying on heat generated by electrical resistance, is considered a fusion welding process because the heat generated melts the metal at the contact points, forming a weld nugget through a phase transition from solid to liquid and back, whereas ultrasonic welding is a solid-state process that achieves bonding without melting. It has long been known that the process of spot welding occurs through the localized melting and coalescence of a small volume of material due to the heating caused by the passage of electric current. The problem with their theory is they offered no experimental proof that you must melt in order to produce a weld. Melts the metal and fuses the two pieces together. Melting and solidification occur between two sheets. It takes a quantified amount of energy to melt a volume of metal that will produce a weld nugget. The fundamental underlying principle of the resistance spot welding process is to join the sheet metal material by melting the interfacial surfaces through the means of Joule heating. Melting, fusion and the formation of a weld. Melting and solidification occur between two sheets. During welding, solidification of a liquid nugget is similar to that in a metal casting. Prior to melting, it appears that solid-state metallic bonding occurs during nugget development. They almost figure out that you don't have to melt in order to weld. Melting and solidification. The material melts, fusing the parts together, at which point the current is turned O. Pressure from the electrodes is maintained and the molten nugget solidifies to form the joint. Forcing a large current through the spot will melt the metal and form the weld. Elihu Thomson's patent US 347, 140 of August 10, 1886 said, "Without the usual necessary application of solders or metals melting at a lower temperature." 94 years before this paper, the inventor of resistance welding already told us do not melt while making a resistance weld. His patent 444,926 of January 20, 1891 said, "Putting on a current capable, if continued, of heating the object beyond the necessary or desired temperature and subsequently and before such temperature is reached diminishing or lessening the current, with the effect of preventing overheating." He clearly knew in 1891 that resistance welding is a solid-state welding process, not a fusion welding process. This book lists spot welding as a solid-state welding process. Expulsion is the forceful ejection of molten metal from the faying surface. When the molten metal meets the air, it burns with loud noise and bright light called expulsion. If we weld without melting the metal, there will be no molten metal, therefore no expulsion. This is what I believe. It doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. The muffler is made out of zinc-coated steel. The evaporation temperature of zinc is 907 degrees Celsius. Since there is no smoke come out of the fang surface during welding, this muffler must be welded below 907 degrees Celsius. This video shows seam welding the outer case of a water heater. The water heater case is also made out of zinc-coated steel. During welding, large amount of smoke come out of the fang surface. This is because the welding temperature exceeds 907 degrees Celsius.
If we have to do this coupon first.
So how many points on the coupon?
Three. Okay. Feel it. And you know it's a good weld when it's tearing away the base material with it, instead of splitting the actual weld. First weld, 6.01. Second weld, 5.88. And your third weld, 6.03.
I welded zinc-coated coupon without smoke. This proves I welded below 907 degrees Celsius. This also proves you don't have to melt in order to weld. The weld lobe normally looks like this. Two curves divide the lobe into three areas. The blue line divides undersized weld or missing weld from acceptable welds. The red line divides the expulsion welds from acceptable welds. Nobody has asked what are the names of those two lines. If on the left of the red line is acceptable weld, on the right of the red line must be unacceptable weld. On the right is expulsion weld, on the left must be non-expulsion weld. Expulsion weld is a fusion weld, non-expulsion weld must be solid-state weld. Solid-state weld is a not melting weld, fusion weld is a melting weld. The line divides the not melting weld, and melting weld must be the melting temperature line. On the right of the blue line is acceptable weld, on the left of the blue line is undersized weld or missing weld. The blue line must be the minimum coalescence temperature line. In Elihu Thomson's patent US 444, 926 he called it necessary temperature line. In another word, acceptable weld is a non-expulsion weld, solid-state weld, and not melting weld. Expulsion weld is an unacceptable weld, fusion weld, and melting weld. If you weld a non-expulsion weld, you have proven you don't melt in order to weld once. I have made about 50,000 non-expulsion welds from 2003 to 2006, it means I have proven you don't have to melt in order to weld 50,000 times. Since melting weld and non-expulsion weld are on the opposite side of the red line, a melting non-expulsion weld cannot exist. Solid-state welds, formed without melting the base materials, are achieved by applying pressure, and sometimes heat, over time, allowing atomic bonding to occur across the interface. The pressure is used to keep the molecules of the two plates within atomic distance of each other. The elevated temperature is needed to increase the mobility to diffuse. Enough time must be allowed so enough molecules can diffuse to the other side to form a weld. Solid-state diffusion bonding is a process by which two nominally flat interfaces can be joined at an elevated temperature, about 50% to 90% of the absolute melting point of the parent material. Since resistance spot welding is also a solid-state welding process, it can also weld between 50% to 90% of the melting temperature. The absolute melting temperature of steel is 1500 degrees Celsius. You can weld a resistance spot weld between 750 degrees Celsius to 1350 degrees Celsius. The minimum coalescence temperature of spot welding steel is 750 degrees Celsius. This is a table documents a constant time, variable current experiment. The weld cap used is a 6.5 mm diameter B cap. The weld time is 170 milliseconds. The force used is 500 pounds. I started welding with 9.2 kA and the nugget diameter is less than 5.00 millimeters. At 9.4 kA I started to have nugget larger than 5.00 millimeters. I kept increase the current until the first expulsion that occurs at 12.5 kA. Current higher than 12.5 kA all welds are expulsion welds. I convert the current to current density so this table can be used for weld cap that has a different diameter. The first acceptable weld occurs at 283 ampere per square millimeter and first expulsion weld occurs at 377 amperes per square millimeter. The midway point is 330 amperes per square millimeter. If you weld between 300 to 330 amperes per square millimeter, you will always weld a good quality weld without expulsion. This is a plot of current density versus temperature. At 300 amperes per square millimeter the temperature is about 820 degrees Celsius and at 330 amperes per square millimeter, the temperature is about 1000 degrees Celsius. If you can keep on welding between these two current density you can eliminate all expulsions. This is the weld lobe built with the data from the table. The low temperature ranges from 750 degrees Celsius to 907 degrees Celsius. 907 degrees Celsius is the evaporation temperature of zinc. Medium temperature ranges from 907 degrees Celsius to 1200 degrees Celsius. At 1200 degrees Celsius you will start to have dendrite and heat affected zone. High temperature ranges from 1200 degrees C to 1500 degrees Celsius. At 1500 degrees Celsius metal starts to melt, expulsion occurs. The first kind of weld is formed between 750 and 1200 degrees C. It is either a low or medium temperature weld. This kind of weld has no dendrite and no heat affected zone. It is the strongest weld possible. The second kind of weld is the high temperature weld. The center dendrite is the part exceeds 1200 degrees Celsius, a medium temperature part surrounds the dendrite. The outside layer is the low temperature weld. The dendrite is weak and brittle. The weld is held together by the medium temperature weld. This weld is stronger than expulsion weld but not as strong as low or medium temperature weld. The last kind of weld is the expulsion weld. It is the weakest weld among the three welds. It lacks quality and consistency. And it also uses about 4 times the energy to make compare with a 850 degree weld. When cook a steak you have 5 stages. There are rare, medium, medium well, and well done. The rare steak is cooked to about 120 degrees Fahrenheit and well done steak is cooked to above 160 degrees Fahrenheit. To cook a well done steak you have to go through rare, medium, medium well and finally well done. A well done steak is nothing more than an overheated rare steak. Making a resistant spot weld is like cooking a steak. It takes the following steps. First you have surface breakdown, then undersize weld, crossing coalescence line, low temperature weld, medium temperature weld, high temperature weld, and melting and expulsion. This makes the expulsion weld an exploded low temperature weld. Welding is a fabrication process that joins materials, typically metals, by using heat, pressure, or both, to create a strong, permanent bond. A weld is a welded joint. A joint is a place where two things or parts are joined. A spot is a particular place or a small round mark. Resistant spot weld is a particular location that a small round spot is joined together by resistance heat. In spot welding, a weld nugget is the circular area of fused metal that forms where two pieces of metal are joined together by applying pressure and heat from an electric current. Nugget is the little round button left on one of sheet after peeling. A nugget does not exist before peeling. This is like the chicken and egg relationship. Only after an egg is hatched it becomes a chicken. Before peeling you have a weld, no nugget. After peeling you have nugget but no weld. A resistant spot welding process, in regard to nugget growth and weld formation, can be divided into several stages. According to Dickinson, these stages are surface breakdown, asperity softening, temperature rising, formation of molten nugget, nugget growth and mechanical collapse, and expulsion. Yes, in solid-state welding, joining occurs at the fang surfaces, the surfaces in contact, not on the surface itself, through processes like pressure and heat below the melting point, without adding filler material. Since resistance welding is also a solid-state welding process, the joining only happen at the fang surface, not in the parent material. This cross-section has no solidified molten metal, yet it is still a very good weld. When you peel this weld you will have a high-quality nugget. The center part of this weld is not solidified molten metal. It is a high-temperature weld. The dendrite is just the overheating part of the parent material. It is not melted.
Three grams of adhesive. 1 hour. $208 tons. Only one brand can make that math work.
Expulsion-free weld controller/monitor is a closed-loop controller. It uses the tip voltage as feedback to keep the weld temperature constant. During programming phase the weld schedule, current density and time, is transformed to a reference temperature. In auto mode, after each weld the weld temperature is compared with the reference weld. If the weld temperature is higher than the reference temperature the current decreases by 100 amperes for the next weld. If the weld temperature is lower than the reference temperature the current increases by 100 amperes for the next weld. That is why you see the current goes up 100 amperes and goes down 100 amperes for the next weld. This way U welds is limited within ± 12.5 degrees Celsius band. Use shaft and increase/decrease switch to adjust the current 9.9 kA. Use shaft and up/down to adjust the weld time to 200 milliseconds. The capture/store switch in capture position and manual/auto switch in manual position. Make a few welds and peel them. If you are satisfied with the nugget size, switch to store and auto. You have programmed to weld at this temperature. In auto mode welding, the manual/auto switch in auto position and capture/hold in hold position. The red light indicates whether you are welding open loop or close loop, or your tip wire is broken or not. Middle white light indicates whether a weld will be made or not. This group LEDs is used to emulate the bright light of expulsion. Without this light, people will have fear of missing weld. The green light tells you whether your weld is a good weld. Use tip wire voltage to calculate the weld temperature through heat equation. The feedback is a temperature which is independent to all other variables. The current is adjusted to keep the weld temperature. By welding at a low or medium temperature, every weld is a good solid-state weld without expulsion. Because everything is calculated based upon mathematics and physics, I can predict the nugget diameter and electrode diameter of every weld. The change of electrode area is automatically compensated by welding at constant temperature. Save at least 3/4 of the energy used on the weld line. All measured parameters can be documented at a central location. "12 years after I welded my first weld, I finally was able to close the loop to weld constant temperature welds. I programmed the temperature at about 850 degrees Celsius, which was 10.0 kiloamperes, 200 milliseconds with a 6.5 mm B cap. The force used is 500 pounds. After welding 2 coupons or 6 welds, I welded 50 welds on 2 10-inch by 12-inch sheets. At that time I also cleaned the cap surface with a wired brush to get rid of zinc deposit. The second day I welded another 566 welds. At weld 1120 the cap diameter was 7.42 mm. And the end of 1240 welds the cap diameter was 7.51 mm. The starting current was 10.0 kiloamperes, and after 1240 weld the current increased to 13.2 kiloamperes. The increase of current is used to compensate the increase of cap diameter. This way the temperature will be kept constant. I started welding in 2003. At that time I was told a $13 million 5-year project had just failed to produce anything useful that can be used to eliminate expulsion on the assembly line. Intelligent resistance welding. Develop intelligent, computer-controlled technologies and systems to improve the quality and consistency of resistance welding for aluminum and conventional, high-strength, and coated steels. Project duration, September 15, 1995 to September 14, 2000. Total project, Est, $13,068,000. Because automakers lack confidence in the quality and consistency of welds, a car may contain up to 30% more spot welds than called for in the specifications. In addition, assembly plants sacrifice about one vehicle body each day for destructive testing to assess the quality of between 2,000 and 5,000 welds in the typical car. The Intelligent Resistance Welding Consortium, in cooperation with the Big 3 U.S. automakers and 5 research organizations, will undertake an effort to develop the knowledge base and then the underlying technology needed to characterize and control all the factors that affect the quality of welds. They will develop sensor-based process monitoring and control systems that keep key process variables within the ranges required to achieve high-quality welds. A key element is the development of neural network models that mimic the behavior of the welding process. In addition to the automotive industry, the U.S. furniture and appliance industries are among the beneficiaries of intelligent resistant welding technology. Even a 10% reduction in the number of spot welds would translate into annual savings of several $100 million for U.S. automakers. For U.S. suppliers of welding equipment and controls, the technology expected to stem from the project would increase competitiveness in a $1.1 billion world market. 5 research organizations are DuPont Central Research, University of Michigan, Battelle, Edison Welding Institute, and Northwestern University. Other welding-related companies were also a member of the consortium. First, none of the partner companies had declared they have found the magic formula that can eliminate expulsion. 3 years after the end of this project, one of the partner companies got $500,000 from my company and $1,500,000 from Ford to eliminate the expulsion weld. If they were successful, they would tell everybody about their success. They did not say a word about their participation of intelligent resistance welding project. I guess they have failed. The most important clue that they have failed come from a 2004 paper sponsored by the consortium. All of these efforts are generally for expulsion detection only. Thus, correcting welding parameters to avoid expulsion, if possible at all, can only be done for subsequent welds after making the initial weld. Therefore, the effectiveness of these methods in eliminating expulsion is limited. What they were really saying is, we started trying to correcting welding parameters to avoid expulsion, but we found out we don't know how to do it, so we have to scale back to monitoring. And the only way we know how to avoid expulsion is to first make an expulsion weld, then reduce the current slightly to avoid another expulsion. We don't think build an adaptive weld controller is possible. A resistance spot welding process, in regard to nugget growth and weld formation, can be divided into several stages. According to Dickinson, these stages are surface breakdown, asperity softening, temperature rising, formation of molten nugget, nugget growth and mechanical collapse, and expulsion. What they were saying is between melting and expulsion there is nugget growth and mechanical collapse. If we can find a weld schedule that stop after nugget growth, then we can melt the metal, still have no expulsion. Unfortunately, melting and expulsion are the two sides of the same thing. A melting non-expulsion weld does not exist. This paper is sponsored by Intelligent Resistance Welding Consortium. All other welding experts were looking for a melting weld that is also a non-expulsion weld. I was just looking for a non-expulsion weld. To make a low or medium temperature weld, all you have to do is heating an area below the electrode above the minimum coalescence temperature. Elihu Thomson called this temperature necessary temperature. This area is indicated by a thin red line. From the top looking down, you can see the center temperature is higher than the temperature at the edge of the electrode. The diameter of the electrode is d and the diameter of the weld is slightly less than the electrode diameter. The difference between the electrode diameter and weld diameter is called transition ring. It is plotted with green color. The inside edge of the transition ring is always 750 degrees Celsius. The outside edge of this ring is the ambient temperature. When the transition ring reaches zero, expulsion occurs. The thickness of the weld is only a few micrometer. When you look at steel weld to steel, the diffusion zone cannot be seen. However, if you weld to similar metal, the diffusion zone is clearly visible. Welding aluminum to nickel, the diffusion zone or thickness of the weld is only 0.3 to 0.6 micrometer. In this diagram, the heat generated at the faying surface leaked through several different paths. Majority of the heat leak through top and bottom sheets to the water-cooled electrodes. The leak to the ambient is very small, we don't have to worry about it. The leak to the metal sheet horizontally is the reason we need a transition ring to insulate the weld and metal sheets. Just like a water heater, we need an insulation layer to insulate the heater core from the outside. This way the heat from the hot water will not leak to the ambient. Assume the metal surrounds the weld is 0 degrees Celsius. The energy to heat the weld to a certain temperature can be calculated like this. Let us assume the imaginary nugget is surrounded by 0 degrees Celsius metal. And the conductivity is represented by a constant K. The capital T is the temperature of the weld. The energy needed to heat the fang surface can be calculated by integrate kT dt from 0 degrees Celsius to any desired temperature. This shows the energy needed to heat the fang surface from 0 degrees Celsius to 1500 degrees Celsius is 3.13 times the energy needed to heat the fang surface from 0 degrees Celsius to 850 degrees Celsius. Assume the latent heat energy used to melt the metal equals the E850. Then it takes 4.13 times the energy to make an expulsion weld than an 850 degrees Celsius weld. A weld with 6.5 mm cap 10 kA and 200 milliseconds measured at the tip wired to be 2200 joules longer weld time, larger weld caps, and thicker stack height all increase the energy to weld. So I just assume the average to make a 850 degrees Celsius weld is 4000 joules. The weld gun and inverter usually have an efficiency of 25%. At kilowatt-hour meter level you use 16,000 joules. Assume an expulsion weld uses 4 times the energy as an 850 degrees Celsius weld. Then an expulsion weld uses 64,000 joules. And the energy saving per weld is 48,000 joules. The Intelligent Resistance Welding Consortium project brief said, because automakers lack confidence in the quality and consistency of welds, a car may contain up to 30% more spot welds than called for in the specifications. It also said, even a 10% reduction in the number of spot welds would translate into annual savings of several $100 million for U.S. automakers. If a car has 5,000 weld and all of them are expulsion welds, when you switch to weld 850 degrees Celsius welds you only need to weld 4,500 welds. The energy saving per car equals 64,000 times 5,000 minus 16,000 times 4,500 equals 248 million joules or 68.9 kilowatt hours. In United States we made 10.3 million cars in 2023. The energy saving could be 925 million kilowatt hours. Worldwide car production in 2023 is 94 millions. The saving worldwide could be 8.45 billion kilowatt hours. How to use closed loop result to program open loop to weld at low or medium temperature. Current stepper welding is a technique that adjusts the current during spot welding to compensate for electrode wear. This method can improve weld quality and reduce spatter. If you weld mostly expulsion welds, the current stepper method does not work. This is because expulsion weld is not a controlled weld, the changes of electrode area cannot be predicted. Only when you weld low or medium temperature welds, you can calculate the contact area change versus the number of welds after tip dressing or change electrode. If you weld mild steel to mild steel, the change of contact area is very small, it can be neglected. If you weld galvanized steel to galvanized steel, then you can see the change. The area change can be calculated using trigonometry. The cap I used in this experiment. The diameter of the sphere is 5/8 of an inch. or 15.88 millimeters, or the radius equals 7.94 millimeters. Out of 1,240 welds, only one expulsion weld and no missing weld. The diameter of the contact surface increased from 6.5 mm to 7.51 mm, and the current increased from 10.0 kA to 13.2 kA. If we increase the current every 38 welds, we can weld 1,000 non-expulsion welds in a row. We only need to tip durst the current 2,500 welds. Theta 1 equals arc sine 6.5 divided by 2, then divide by 7.94 equals 24.16 degree. x1, the distance from the center of the sphere to 6.5 mm surface, equals 7.94 times cosine 24.17 degree equals 7.244 mm. Theta 2 equals arc sine 7.51 divided by 2, then divided by 7.94 equals 28.22 degree. x2 equals 7.94 cosine 28.22 degree equals 6.996 millimeters. The distance between 6.5 mm surface and 7.51 mm surface divided by 1,240 equals 2 times 10 to the minus 4 mm, or 0.2 micrometer. Each weld will peel off this thickness of copper from the surface of the electrode. From this, if you give me the weld number, I can tell you what the surface area at that weld. With this information, you can weld at a constant current density without feedback loop. If you set the weld schedule based on this, you can eliminate all expulsion welds. We can build a spreadsheet, use this information. The 300 is the current density, 7.244 is the distance between 6.5 mm surface to the center of the weld. At weld 1,240, the area is 44.30 square millimeters and the current is 13,200 amperes. In this spreadsheet, current increased every 38 weld. And the blue shaded area is the number of weld versus area. All you have to do is to multiply the current density to the area. You will get the exact current at that weld in order to keep current density constant. In this spreadsheet, the first part of the spreadsheet exceeds 100 ampere per 38 welds. We need to reduce the number of welds for every 100 amperes. If we add 100 amperes every 37 welds, the current density will stay constant. Most of the people use a 6.35 mm or quarter-inch B cap to weld. The X1 has to be recalculated and the start current has to change also. This new spreadsheet looks like this. Welding at 310 amperes per square millimeters. And add 100 amperes every 36 welds. Welding at 320 amperes per square millimeter. Add 100 amperes every 35 welds. Welding at 330 amperes per square millimeter. Add 100 amperes every 34 welds. Ford's approach for creating the lightest car has been to plunge headfirst into the aluminum trend. The company spent a little over $1 billion overhauling several manufacturing plants in order to build new facilities equipped to work with aluminum. According to Car and Driver magazine, the company relied primarily on the rivet bonding process instead of spot welding, which is more commonly used within the automobile industry to join aluminum alloys. Rivet bonding is a process that uses adhesives and fasteners to join metals. In this process, a metal bonding adhesive is applied to the interface of two aluminum plates. The bonded pieces are then squeezed together using a rivet bonding gun. The truck's frame is comprised of 78% high-strength steel, but there's very little steel to be found anywhere else. In fact, just about everything you see on the outside of the 2015 F-150 is aluminum alloy. Although the 2015 F-150 is much larger than the 2014 model, its use of aluminum has made it significantly lighter. In fact, the 2015 F-150 is a whopping 700 pounds lighter than the 2014 version. A friend of mine who had this truck told me that the aluminum panels were 1,100 pounds lighter than the steel panels they repaced, but the steel rivets used weigh 400 pounds. That is why the net weight saving is only 700 pounds. Welding aluminum to steel using ultrasound is very easy. The oxide of aluminum is destroyed by the ultrasonic friction. In the video, the coupon that bends is aluminum. The coupon that stays straight is steel. Welding dissimilar metals in diffusion bonding is very easy. This picture shows aluminum welded with titanium. This picture shows in order to weld aluminum to titanium, the temperature has to be between 520 to 550 degrees Celsius. In resistance spot welding, it is impossible to control the temperature this close. This is why it is very difficult to resistance weld aluminum to steel. Few years ago when I tried to weld mild steel to aluminum, the first weld melted a hole through aluminum and destroyed the electrodes. But when I tried to weld aluminum to galvanized steel, it only took me 30 minutes to find the right weld schedule and welded 5 coupons. The only difference between mild steel and galvanized steel is the zinc layer. I later found out the zinc layer changed the normal resistance welding to transient liquid phase welding and helped to join aluminum to steel. Transient liquid phase welding refers to a joining process where a temporary liquid phase is created between two materials using an inner layer, which then solidifies through diffusion, resulting in a strong bond with a microstructure similar to the parent material, often used for joining dissimilar metals at relatively low temperatures compared to conventional fusion welding techniques. Essentially, the liquid phase transiently exists during the bonding process and then disappears as the inner layer atoms diffuse into the base materials, leaving a solid joint behind. The eutectic temperature of zinc and steel, which is primarily iron, is not a readily available value because steel is a complex alloy and its interaction with zinc creates a ternary system, making the eutectic point dependent on the exact composition of the steel. However, when discussing zinc with a steel-like composition, the relevant eutectic temperature is typically considered to be around 380 degrees Celsius, 716 degrees Fahrenheit, which is close to the eutectic point of a zinc-aluminum alloy often used in galvanization processes. The reason that I cannot weld mild steel to aluminum is the coalescence temperature range is only from 520 degrees Celsius to 550 degrees Celsius. The coalescence temperature range of galvanized steel and aluminum is between 380 degrees Celsius to 550 degrees Celsius, which makes welding aluminum to steel much easier. Welding aluminum to mild steel is solid-state welding. Welding aluminum to galvanized steel is transient liquid phase welding. If we can replace rivets with welding and joining the frame to aluminum body panels, we can save the weight of steel rivets. Because I was self-funded, all I can accomplish was to show that to weld galvanized steel to aluminum with spot welding is possible. Additional research to weld aluminum to steel has to be done by somebody else. A small mistake, big disaster refers to a seemingly insignificant error that, through a chain of events, leads to a large-scale catastrophe, often illustrating the butterfly effect where a minor change can have major consequences, essentially, a tiny mistake escalating into a significant problem. The Space Shuttle Challenger disaster occurred on January 28, 1986, when the shuttle broke apart 73 seconds into its flight. The explosion killed all 7 crew members. According to Richard Feynman, the primary cause of the Challenger disaster was a failure of the O-rings in the solid rocket boosters, specifically due to their loss of elasticity in the cold launch temperature, which led to a breach in the seals and ultimately the explosion of the shuttle, essentially, a design flaw exacerbated by the cold weather conditions at launch. The Mars Climate Orbiter mission failed due to a critical error in unit conversion, where a software program used to calculate the spacecraft's trajectory was not properly translated from English units to metric units, causing the orbiter to enter the Martian atmosphere at the wrong angle and burn up upon entry. Essentially, a metric mishap is what led to the loss of the spacecraft. Yes, in the context of spot welding, expulsion is widely considered the biggest failure because it signifies the ejection of molten metal from the weld nugget, significantly weakening the joint and compromising its structural integrity, essentially meaning the weld is not properly formed and could easily fail under stress. Solutions are often hidden in plain sight, waiting for the right perspective to uncover them. John Nash. We have suffered close to a century of mediocre welds, wasted billions of kWh of energy each year by making expulsion welds. The reason is because most of the welding professionals still believe that you have to melt in order to weld. To eliminate all expulsion from the assembly lines, all you have to do is to program your controller to weld at a fixed current density. If you follow my suggestions, you will easily make 1,000 welds without expulsion.